Hi guys, welcome back to the channel. Hope you all are doing well. Today we're going to design a video application such as YouTube. An application like YouTube can have many different features, but to keep things simple and easy to understand, I'm going to be mainly focusing on three distinct features. The first feature is going to be uploading a video. The second one is going to be how a user can watch or stream a video. And the third one is going to be how you can support the same video in multiple different resolutions and formats in your backend. So before we dig deeper into the architecture, let's take a look at a more high-level view of the whole system. At the top, you have the client, which is going to be your user using their browser or phone. To the left is going to be our CDN. The browsers are going to primarily use our CDNs to stream the videos from. This means all the video files itself, the video file themselves, they are going to be stored in CDN as opposed to our backend. To the right, you can see the API servers. These are going to be all our backend API endpoints, our databases, caches, message bus, and everything else. So the part we're going to focus the most on is going to be the API server, but I think it's important to know there's also the CDN and the client. All right, so the first thing we're going to take a look at is the backend APIs. Of course, once again, a system like YouTube can have many different APIs for it to work properly, but to make things simpler, we're going to break it down into two different endpoints. The first one that you see over here, this is our get endpoint, which is going to give a list of videos for a user to consume. Let's say you're a user with user ID 12345. Then your browser, once you go to youtube.com, it can make a request to our backend. It's going to be a get request to the video feed endpoint, and we're going to pass in the user ID as a query parameter. And then the backend can give a JSON blob with a list of videos that the user can watch, right? And the second API is going to be a post endpoint. I'm just calling it a /video, and in the request body of the post request, you're going to have the video file data. This is the endpoint that the user is going to use to upload a video to our servers. Okay, so let's take a look at how the uploading a video is going to work. The first thing we're going to take a look at is a more zoomed out view. So this is going to be a simple implementation, and then gradually we're gonna build on top of it. So this is gonna be similar to the other system design videos that I have in the channel. So if you understood how those kind of worked, this should also be easy. The first one you see, I'm gonna zoom in a bit. There you go. All right, so we're gonna look at the top, which is the client. This is gonna be the phone or the browser of the user. And let's say they wanna upload a video file on YouTube. They can go ahead and maybe we can have a button called upload video or something that opens up their file browser. And let's say they choose a file and then hit the upload button. The moment they hit the upload button, that HTTP request that gets triggered, in our case, it's going to be that post request to the videos endpoint. This is going to hit the load balancer. The job of the load balancer is to forward the request to the correct API server. That's what you see over here. So the load balancer is forwarding to the API server. When we are at the API server, what the API server is going to do is parse out the binary object of the video file. So this is going to be the whole video file, but in a binary format. It's going to store that file into Amazon S3. Amazon S3 is just a file storage that you can use to store the file directly instead of storing the whole video in like a MySQL table or something. Once the file is stored in Amazon S3, the API server is going to store the related metadata to a relational table like a MySQL table or a Postgres table. We are going to talk about both the S3 and the MySQL table in details, but this is in a very high level how uploading a video can work in your backend. If you want to keep things simple, you can literally just have this design and it should work just fine. But when we're talking about an application in the scale of YouTube, or even like any application where you'll get quite a lot of users, you want to break it down further and have a more robust system. So now let's talk about the different things in the diagram here, right? So the first question you might have is, how is the client sending the video information to the servers? And it's going to be pretty straightforward. The post request that you see over here, that is going to have a request body, and that the file that the user is uploading is going to be in that request body as a binary data. For smaller files, that should work fine, but for larger files, you might have to do like a multi-part file upload. There are different ways to do it, but in this case, we're just going to assume that when you're uploading a video, your video should be able, the video can be contained within that one HTTP request. The next question might be, what is the load balancer doing? The load balancer that you see over here. Our backend, which is composed of different API servers. Of course, we're going to be running multiple different instances of the same API, and it's the job of your load balancer to decide which instance does it want to route the request to. This can depend on a lot of things, like if a particular instance is unhealthy or not, or if an instance is having too much difficulty serving a lot of requests. So the load balancer can have different logic implemented within it, and it can use that to decide which instance to route the request to. All right, and then we're gonna focus on this part number 3, which is gonna be stores the original file. So let's see, what does that exactly mean, right? Storing the original file. So that means that we need a place to store the raw binary data of the video. Because when your backend is getting it, it's getting the whole video as just binary data. And you want to store this binary data somewhere. Of course, you can store it in a database like MySQL, Postgres, or even like a Cassandra or something. But it's not really a good practice to store large objects like videos or even photos in database. There are multiple different reasons. I think I have another video explaining that, but what the takeaway should be that if you're storing large objects like even like PDFs or images or videos, you want to store them in a blob storage like Amazon S3. So that's why we were storing the file in S3 as opposed to like MySQL or Postgres. The next question might be, what is the video metadata? In number 4, you see we have the step called store metadata. So this is when the API server is storing some metadata related to the video into a relational table. Let's talk about what this metadata can be, right? So when a user is uploading a video, of course, apart from the video file itself, there are many different details related to the video. We're calling those the metadata of the video. Some examples of the metadata can be the thumbnail. So this is the thumbnail that you see on YouTube. It can be the video title, the description, the different tags associated with the video, and of course the user ID of the user who just uploaded the video, and at the end the URL, because if you're storing the video itself on S3, of course you have a URL to go and get that video, and you want to store that URL with the video metadata, so that let's say when someone wants to watch a video of with an ID of 5, that table, the video metadata table, can be easily queried to find the S3 URL where the user can go and watch that video with ID 5. All right, and then the next question might be that why are we storing our metadata in MySQL as opposed to some other database? Honestly, it doesn't have to be MySQL. It can be any relational database. It can be Postgres or any other relational database of your choice. I don't really see a reason of why we would want to store it in a non-relational database, because the data format is very simple and predictable. The write throughput shouldn't be as high as read throughput, because of course you can have tons and tons of people watching videos on YouTube, but you don't really have the same number of people uploading videos. So given the throughput of write is going to be comparatively low, I think a MySQL table can just handle it fine. Relational tables like MySQL gives you transactional guarantees, so it's much more simpler when you're writing to it. You don't have to worry about losing data or not being consistent enough. And lastly, for our relational table like MySQL or Postgres, even though they are difficult to scale horizontally, like you can a Cassandra table or some non-relational table, still given the schema of our data, it should be easy to scale. You can easily partition or shard your database by the user ID or maybe like the video ID or something like that. So it should be pretty straightforward to divide your one instance if you want to like partition your data into multiple different shards. If you don't want to shard your database, you can just have a bunch of replica. So if you're following a leader-follower architecture, you can have all your writes going to the leader, and then you can have multiple follower, which are going to be your replicas of your database. And all these replicas can serve all the reads at the same time. Of course, you might run into some replication lag of when you have a leader-follower architecture in a relational database structure. But given a video upload, it's reasonable to have a tiny bit of replication lag. But yeah, I don't think you'll really run into a lot because the upload is going to be significantly lower than the watching. So those are, I'll go back to the diagram. Okay, so that's going to be the first step in designing this system. So to give you a summary, we have the client that's making a post request to our videos endpoint. That request is being routed to the correct API server by the load balancer. Then the API is storing the raw video onto Amazon S3, which is a blob storage. And then it's storing all the metadata related to the video, such as thumbnail, description, title, into a relational table like a MySQL or a Postgres. All right, so now, of course, there is more to the system than what we just talked about. So let's look at some of the things that we are yet to look at, and then gradually we'll start looking at them one. The first thing we did not talk about is the schema of the table, so the metadata table. We talked about some fields that can be there, but we're going to take a look at the schema. We did not talk at all about the different transcoding formats. So how are you going to transcode a video to different formats, and how is all that going to work? We did not talk about how is the copyright check going to work, because when you're uploading a video on YouTube, if it has any audio or clip from other videos and you don't have the rights to have them in your video, you can get a copyright strike. So we're going to talk about how you can implement something like that. Also CDN, at the beginning of the video, I mentioned that the users are going to be streaming the video from the CDN, but we did not really talk about how it's going to work. So we'll take a look at that too. And lastly, we didn't talk about how the streaming is actually going to work, because of course you want the user to be able to watch the same video easily and quickly from all different platforms and operating. So those are the things we're going to be taking a look at, and I'm going to start with the metadata table. So for the metadata table itself, we can have multiple different columns. The first one's going to be the ID. This is the ID of the video. Then we're going to have the user ID, which is going to be the user's ID, the user that uploaded the video. We're going to have the title of the video, description, the thumbnail URL. So this can be a thumbnail that is also stored in S3. And then we get that URL and then store it in this table. The original video URLs, of course, if you remember, we were storing the original video in S3, and this is going to give you a URL, and we want to store that URL in the same table. And we're also going to have a different one called the transcoded video URL. This is going to be not the original video URL, but the transcoded one. So the one that is specific to the user's device. And lastly, we can have visibility. So for instance, if a video has a copyright strike and we want to give the owner of the video a chance to remove the copyright content, we can just set the visibility to none or like invisible, so that the the video is not visible in the user's feed. So yeah, that's going to be our metadata table. Of course, you can add more columns to it, but hopefully this gives you an idea. And as you can see, the schema is very straightforward for the video metadata table. So we're not really thinking of any more complex databases. A relational table will work just fine for us. Now the next thing is going to be transcoding. So how does transcoding work, and what do I actually mean by transcoding? Your original video file has a certain format, right? So let's say when the user is uploading the file, it can be an MP4 file, it can be an AVI file, or any other format that the user actually shot the video in. But this video, it must be encoded into compatible bitrates and formats. This means that there are different devices like Apple device versus Android device versus browsers. Each one of them supports different bitrates and different formats, and your video has to be encoded into those formats for the client to play them to the best of its ability, right? So if you want to ensure a very smooth playback of your video in all devices, you want to transcode them into different bitrates and formats so that when a user is switching between devices, the video can stream properly. Also, this is going to let you support different kind of internet connections that the user might have. A user might have a very, very slow 3G or a very fast 5G. And for the two different speeds, you need two different kind of video quality or video formats. So that the user can watch them equally nicely, right? So that's how transcoding works. In an application like YouTube that is hosted or more like used in so many different devices, you want to be able to support all the different formats. So let's see from our design, how is the transcoding gonna work, okay? So if you remember, this was our original design. So we're gonna take a look at what happens after this point. So our original video is stored in S3 now, and the related metadata is there in the metadata table. Now let's see what happens. All right, so we had 3 and 4, so now we're gonna start from here, number 5. Okay, so once the API server stores the metadata in the metadata table, it can go ahead and make a HTTP call to the transcoding service. This is going to be some other microservice that we have in our architecture, and the job of this service is to do everything related to transcoding. Okay, so our API server is going to make an HTTP call to the transcoding service, and it's going to pass in the S3 URL of the video that needs to be transcoded. Okay, so at this point, our original video is there in S3, and we're giving that URL to the transcoding service so that it can actually read the video file. Once the transcoding service gets a request, all it needs to do is go ahead and write a message in a message queue. In our case, it can be a topic in Kafka. And this message will have maybe the video URL and some other information, so that so the message will have all the information that is needed by the system to actually do the transcoding. Okay, we're going to talk about why we're using a message queue here in a bit. So that's how the messages are going to be written to Kafka, and then you can have a bunch of workers that you see to your right in the green box. So these are going to be very lightweight workers that are consuming this Kafka topic. So it's going to be consuming messages from the Kafka topic. Each message in the topic is, of course, one video that needs to be transcoded. The transcoding workers can go ahead, pick up messages, and for every message, it can go ahead, read the video from S3, do the transcoding, and then once the transcode is done, it goes to step 8 that you see over here. And step 8 is transcoding the video and then storing the transcoded version in S3. This is going to be separate from the original file, because the original file is exactly how the user gave it to us. And the transcoded version is, of course, and it doesn't have to be one version, it can be multiple versions supporting different resolutions and bit rates. So that's what the transcoding worker is going to do. And once the transcoded video is there in S3, it can go ahead and in step 9, you can see it stores in that same MySQL table, it stores the URL of the transcoded video. All right, so now let's dig a bit deeper into the process. The first question might be, why do we need the message queue over here? Can't the transcoding service just do the transcoding on demand when an API request comes in? The problem with that is a process like transcoding can be very expensive and it takes a lot of time. You don't want to block a request while you're processing the whole video. Not only will your client need to wait for a long time for this to happen, but it can also run into different timeouts and different errors if your transcoding service is taking too long. So you want to make the whole process asynchronous so that your other services don't have to wait for this transcoding to finish. Secondly, depending on the time of the day, you can have a lot of people uploading videos at the same time. If a lot of people are uploading videos at the same time, of course, you have a ton of videos to transcode. And if you need something, right? You need something to scale up and down very quickly to grow or shrink with the demand of transcoding. If you put the responsibility of the transcoding to your API server, that means you would have to scale up or down your whole server depending on the load of the system. That is very expensive to do. Instead, you can have these, to the right you can see, you can have these more lightweight Lambda functions or some other Python process. All it's doing is consuming from the Kafka topic and then doing the transcoding. In an hour where you have tons of video being created, you can easily scale up all the transcoding workers that you have. And in hours where there are not a lot of videos being created, you can shrink down the number of instances you have. So it gives you very good elasticity so that depending on the traffic, you can scale up or down the number of transcoding workers that you have. Because you do have to remember, these are workers that can take a lot of resources because the process itself is very expensive. All right. So to give you a summary of all the steps we talked about for the transcoding bit, the first thing your API server is going to do is ask the transcoding service to transcode the new video. It can do that through the API like you see over here, step 5. Or you can also do it more asynchronously. So you can have something like, there are triggers you can use in AWS. So let's say you can say, whenever a new file gets uploaded to S3 in this step number 3, you can trigger some kind of a Lambda function, and maybe that Lambda function can go ahead and publish a message to Kafka instead of your API server making a HTTP call to the transcoding service, which is going to be, of course, more synchronous. So yeah, that's an option too. You can take a look at that. I'm going to put some information in the doc, but yeah, you can do that too. The next step is going to be the transcoding service itself. Once it gets the request, it just writes a message to a Kafka topic that is over here. And the message is just a video URL and maybe some information that the workers might need to actually do the transcode. Step 3 is going to be all our transcoding workers. These are going to be lightweight here. So these are going to be the lightweight workers or Lambda functions or whatever you want to call it. We're going to have those just listening to the Kafka topic. Whenever there's a message, it's going to pull the message from Kafka, do all the computation required for the transcoding, and then it's going to go ahead and it's going to go ahead and upload the transcoded videos to S3. It's going to be a separate bucket. And it's also going to upload the video metadata table with the URLs of those transcoded videos. Okay, so that's how the whole transcoding is going to work. Of course, this is happening sort of asynchronously because we don't really need to block the whole upload request until all these are done, because that's not just realistic. Okay, so the next thing is going to be the copyright check. If you ever uploaded a video on YouTube or any other platform, you know that your video can get a copyright strike. This means that in your video, if you're using any resources like audio or other video within your video that you don't have the right to, it can get a copyright strike, which means it can and most probably will be taken down from YouTube. So let's see how that works. So this is going to be an extension, of course. So over here, you saw we were at the transcoding workers. Now we're going to build it from there. Okay, so here you see the transcoding workers. So the copyright check, this can be done asynchronously. Again, you don't want to do all these synchronously while the user waits. You can kick off the process and give the user some kind of a progress bar while all these things are happening in the background. So for the transcoding workers, once the transcoded video is there in S3 and the video metadata is updated, it can go ahead and call the copyright service. This can be an HTTP call, or it can be more asynchronous, like a Kafka message or something. Yeah, so you can use either. In my case, I'm going with an API call, but if you can make the whole system way more decoupled, that's all the better. So the copyright service is going to be responsible for everything related to copyright. So it's going to have all the logic related to determining if a video has anything, any copyright material in it. If the service decides that the video is copyrighted, it can go ahead and make a call to the email service to go ahead and send the user an email telling them, hey, please change your video, otherwise we're going to delete it. And then it can also go ahead and update the video metadata table. If we have a flag that tells, let's say for every row of video, you have a column which tells you if the video has a copyright strike or not. So your copyright service can go ahead and update that table. And the email service can go ahead and use MailChimp or Braze or something like that to actually send the email to the user. So a few things to note is, let's see. Yeah. So this is where we talked about copyright check, but similarly, you can also do things like checking if the video has any inappropriate content. You can you can do all these in parallel, so you don't really have to block on one thing happening and then the other. I don't have the inappropriate content check in the diagram, but you can imagine that in step 10 over here, you can split this into the copyright route and also the content moderation route. Okay. Ideally, for things like copyright and content moderation, you want to do them before the transcoding step, just because the transcoding step is very expensive. I didn't put them there because I went through everything and then had to stack these after that. But ideally, you would want to have both the copyright check and the content check right before transcoding, so that you don't transcode the video unnecessarily if you know that the video might be taken down in the first place. Alright, so that was all about the copyright check. Now let's talk about CDN, okay? So what is CDN exactly? So CDN is, I think it's called Content Distribution Network. So what it means is you can have your one video in many different CDN buckets. This means that your same video is gonna be in a server, let's say in Europe, one in Asia, one in North America, one in South America. What this lets you do is keep your video files geographically close to the users that are watching the video. Because otherwise, let's say you have a user in Asia and they want to watch a video, you don't want to be streaming that video all the way from North America, right? Because that's going to be very slow and the user might already have bad internet. In that case, you will have your user running into buffering, which is like the video stops while all the bits of the video travels half of the continent to reach the user's computer. So instead, you want to have the videos very close to the user. These can be one per continent. It can be one per city. So it can be literally whatever granularity that you want them to be in. Okay. So you can configure your S3 bucket to support CDN. Okay. So this means, let's go up. Yeah, so in step 8, you are storing the transcoded video in a S3 bucket over here, right? You can, through the AWS UI, or maybe you might have to set up some infra. You can tell AWS that the file I'm uploading over here should be supported through CDN. That means that, and you can configure the CDN so that this one video is there in 5 or 6 different CDN servers. Okay. So yeah, so you can configure your S3 bucket so that whenever you upload a video to that bucket, it's automatically kind of propagated to all the different servers around the world. By doing so, you're making sure that the video file is available at the edge of many locations. So this means that instead, whenever a user wants to watch a video, they don't necessarily have to talk to your API server every single time. They can just get all the video data from one of these CDN servers that is going to be significantly closer to the user compared to your API server. File can be served from server closest to user. We already talked about that. And ultimately, the whole goal of using a CDN here is that the streaming experience of your user is going to be very smooth. They don't have to go through buffering or lagging or just pausing and then playing it after a while. They can just sit there and the whole video is going to be streamed to them very, very quickly. All right. So that is the whole uploading flow. I'm going to talk about watching a video. I think that's the last thing. But to give you a quick recap of the whole thing, I'm going to zoom in. It's better. Okay. I'll zoom in one more. Okay. Let's go to the left. All right, perfect. So this is your whole architecture that we kind of gradually built towards. I'm going to start from the top. This is going to be your client, which is your user, uploading a video through their browser or phone. The client makes an HTTP call, which is a post request to the video's endpoint. The load balancer receives the HTTP request and then forwards it to the correct API server. Now, in your backend, which is the API server, you stored the raw file in S3. This is going to be exactly the file that the user gave to you. And then you're going to store all the metadata related to the video in a relational table like a MySQL or a Postgres table. When I talk about video metadata, these are data such as the title of the video, the description, the tags, the URL of the video in S3, and all those things. Now the API server, either through an HTTP call or just through Kafka or some other asynchronous means, makes a call to the transcoding service and passes in the S3 URL of the video that needs to be transcoded. Transcoding is a very expensive process. So instead of your transcoding service blocking this HTTP call, it's gonna just write a message to the message queue. So this is gonna be a topic within Kafka where all the messages are requests of videos that needs to be transcoded. Once the transcoding service writes a message to the message queue, it can just go ahead and tell the API server, all right, you're good, I'll take care of it. To the right, you have the transcoding workers. These are going to be workers waiting and listening to that Kafka topic and consuming from that Kafka topic. For every message in the topic, it's going to consume the message, do all the transcoding, which is going to be very expensive and might take a long time, but it's going to do that. And then once the transcoding is done, it's going to go ahead and store the video in another S3 bucket. This is going to be a totally new bucket, not the one where you're storing the original video. This bucket will also be supported by CDN, so that this transcoded video that you just uploaded to S3 is also there available in your CDN, which can be distributed all around the world. Once the video is stored in S3, the worker will also go ahead and update the metadata associated with that video in that metadata table that we talked about at the beginning. Once the transcoding is done, it can also go ahead and send the URL to the copyright service. It can do this once again either through a HTTP call to the copyright service, or it can do it through some Kafka topic similar to what we did for transcoding. The copyright service is gonna have all the logic related to determining whether a video has any copyright content. If it does, it can go ahead and make an HTTP call to your email service to go ahead and send the email to the user telling them that the video has copyright content. At the same time, it can go ahead and upload the metadata table, the MySQL or Postgres metadata table, indicating in that row of that video that this video has a copyright strike. Alright, so that's gonna be your whole upload flow. And now let's talk about the next bit, which I think is the last one. Yeah. So the last thing is gonna be streaming the video. Okay. So if you remember, when it comes to streaming the video, of course, the first step is when the user goes to youtube.com, they get a feed of all the videos that is kinda recommended for them. So the client makes a request to that video feed endpoint with the user ID. The load balancer forwards the request to the API server. The API server looks at the user ID, and then it needs to find all the videos that you want to show the user, right? Now that's where our feed system comes in. We already talked about a feed system design, I think, in the previous video. So I'm going to link it in the description below if you want to know how you can compute feeds for users very, very quickly. So I'm not going to go into the details, but the idea is that in some kind of a caching server like a Redis or a Memcache, you can map a user ID to a list of video IDs that the user should see in their feed. That means when the API server is getting the request for a feed, all it needs to do is look at the cache for that user and get the list of videos that the browser should show to the user. Once it gets the video IDs, it goes ahead and makes a very simple select query to your relational table to get all the different data related to that video. Because just with the video ID, the user won't really get any data. You need other stuff like the description, title, thumbnail, the video URL itself, and all those things. So the API server talks to the cache, gets the list of video IDs, talks to the relational table to get all the data. We're calling that step hydration. And now that it has this huge JSON blob with a list of videos, it can go ahead and send all the data to the client. The URLs that are gonna be in the payload for every video is gonna be the CDN URL. So of course, this is gonna be the location. So this is gonna be the video URL from the CDN server that is closest to the user. So let's say if the user is in Africa, the API server is gonna give you a video URL closest to Africa. If it's in Asia, it's gonna be a different URL because this is gonna be the version of the video that is hosted in Asia. So you can see how that works. Okay. So yeah, just to go over it again, it's going to be similar to the newsfeed system design. I'm going to have it linked in the description below. You have the cache for the feed, and the format of the cache is the one you see over here. You can have a key, which is going to be the ID of the user. And then the value can be a list with all the video IDs. Once you have all the IDs that you want to send to the user, you can do a select star from table where video ID in, and then the list of IDs. You can make a simple query like that on your MySQL table, get all the data, which is going to be the hydration step, and then return them to the client. And of course, the CDNs that the URLs that you're returning for every video is going to be the CDN URL so that your user can stream the whole video very smoothly. All right, so hopefully that gave you a good picture of how the whole thing works. This was the streaming side of things, so the watching a video, and then we had this, which was the uploading side, which is of course more complicated than that. If you have any questions about the whole design, I would recommend checking out some of the other videos. I know I have one on notification service, one on a URL shortener, and also a newsfeed service. So I'd recommend checking them out. And if you still have questions, of course, leave them in the comments and I'll get back to you as soon as I can. With that being said, I hope this was helpful. And I also hope you guys have a good rest of the day. And I'm gonna catch you guys in the next one. Bye-bye.